the mobility transition. You all know about the energy transition that we are facing, moving away from fossil to alternative sources. And you have heard many presentations throughout the years that this is needed, and there are many reasons for that. And that is not the subject of what we are going to hear today, because now we are going to talk about the role of nonwovens in this mobility transition. Nonwovens are essential for the mobility transition is the title of our seminar. I have two speakers. At your and my left, Ian Dowdall. He is going to talk about the role of nonwovens in battery separators. So it sounds kind of technical, but it's not meant to be super technical. In today's seminar, he's going to show you the relevance of nonwovens in batteries, battery technology. The second speaker, that's Siddharth Shukla. He will be speaking about the role of nonwovens in fuel cell technologies. So there we have these two different technologies. So it will be an exciting seminar. Let's move to the first one. I introduced to you Ian Dowdall, as said. He's educated in the UK, studied applied chemistry at Coventry University, worked for a long time with the Pell Corporation for 22 years, known for its filtration activities. And the last 9 years he spent working at Hollingsworth and Vos Energy Solutions business unit, responsible for sales marketing of all products in EMEA. And today he speaks as the European product manager for HMV, covering both filtration and energy solutions. Please join me in welcoming Ian on the stage.
Thank you. Thanks for the introduction. I can assure you this won't be a technical presentation. I'm going to try to keep it as lively as possible without talking too much about the actual technology of making a non-woven AGM separator and the other kind of things that we're going to be talking about. So I have been in the industry now for about just under 10 years, working with HMV. What we're going to talk about just briefly, I'll give you a bit of an introduction into what the technology is all about. It's already been established that we're going to talk really more about batteries than anything else today in my part of the presentation before the fuel cell part. I'm going to talk a little bit about the global battery market to show you where the battery market's moving, some of the reasons why it's moving as it is, which, you know, really looking at cars, light vehicles, and the way things are moving within that market. Have a little brief look at the role of a battery, what a battery does, and how it does it. And then we're going to talk a little bit more then. I guess when we talk batteries and we talk vehicles, we're often thinking about lithium-based batteries. I'll touch lithium-based batteries a little, but then we'll talk about the good old-fashioned lead-acid battery that's been around for 160 years and is really playing a really important part in this transition and supporting the performance of a lithium battery. Where nonwovens fit, and then a little bit, depending on time, where the future may be for this kind of technology. So 10 seconds on HMV. I think most people will have heard of HMV, long-standing company in nonwovens, and I think that, you know, just looking around in the exhibition, we can see lots and lots of applications where HMV are involved in supplying media. So we've got 13 sites basically globally. I work from the UK. And we also have sites in Germany and across the world. Okay, so let's talk a little bit about the global battery market. The slide's quite busy. I want to really focus on the two technologies, lithium technology and lead-acid technology. But it's worth mentioning that battery chemistry, if we think about it in four sections really, We've got lithium technology, we've got lead technology, we've got sodium, and we've got nickel. So there are four major technologies, but the market really is dominated by lead and by lithium as lithium grows. So we've got a 20-year time span on that chart. As you can see, the dark portion, which is the lithium for XEV, so for cars, for the transportation market, starts off quite small and then just explodes. And lithium for others, which is kind of an orange bar there at the top that says 23.2. That's everything else that uses lithium batteries. So really does become a two-horse race, with lead representing about a third of the global battery market by about 2030, and lithium representing the rest, with a few other small exceptions. Who knows what's going to happen in the future? People are working on lots of experimental technologies now, but lithium looks like the one that's going to prevail, particularly for the traction part of cars, light commercial vehicles. Okay. I'm going to talk mainly about the non-woven opportunities that exist in the lead-acid market, and there are a few, and they're quite interesting and quite a difficult or a simple-sounding product, but with some real intrinsic benefits to it. Okay, so again, I think we've all seen these kind of charts in the past. This is the way that the light vehicle powertrain's growing over a period from kind of 3 or 4 years ago all the way through to 2040. The information before the line is based on a company called IHS that does market research in automotive, and from 2027 onwards, this is some internal research that we've done within H&V along with Bloomberg. As we can see, in 2019, the hybrid, the battery electric vehicles, anything that had electric propulsion, it was very small. The market was dominated by start-stop. So the start-stop technology is the technology that's really started the decarbonisation in automotive. Vehicles are responsible for a huge amount of the carbon dioxide production, and start-stop technology really started to reduce that by 10% and more. Interestingly, the non-woven part of the AGM battery is the thing that's really enabled it to perform that function. As we move forward, the electrification part starts to accelerate, pardon the pun, and by 2040 we expect that just about everything will have electric power. Of all those vehicles that are around in 2040 will also have a 12-volt battery. So a little bit about the light vehicle powertrain. Tends to be powered by a 48-volt lithium-based battery, but it's also got a 12-volt system in it, and I'll come across that in a moment. The 12-volt system will probably, we expect, 90, 97, 98% of the 12-volt systems to be powered by lead-acid batteries, even in 2040. So let's talk about a battery. What is a battery? Very simply, it contains an anode, a cathode, electrolyte, and a separator. Again, I'm probably doing battery scientists an injustice here by making it sound so simple, but that's what it is. The separator is inert. It doesn't have any chemical properties, but it does enable the battery to perform whichever battery chemistry we're talking about. It is an enabler to enable the product to work, the battery to work properly. So, as I say, the cell contains a separator that's not active, but it really is key to performance. And again, I'll talk a little bit about that as we move through the presentation. Types of battery. There are lots of choices that people who are designing systems have got to choose from batteries, all the way down there from, so we're talking here two charts. One is energy density and one's power, basically, so the ability to deliver energy and the power that the battery can contain. A comment there: among all secondary battery chemistry, lithium-ion and lithium metal batteries offer the best energy and power density compared to weight. Secondary batteries are simply rechargeable batteries. Primary batteries are not rechargeable. So primary batteries tend to be used in things like remote controls, in this kind of thing. Don't need a lot of power. Secondary batteries are there, and they are rechargeable. So on the chart there, you can see the lithium-ion or the lithium-based batteries. Lithium-ion, we describe lithium-ion batteries as lithium-ion because it's the lithium ions that do the energy transfer that go from cathode to anode. So on the face of it, for drivetrains, for power systems, lithium's going to win. Lead acid there, sitting in the bottom. It's been around for 160 years, and it's been developed and developed and developed. And again, what we'll talk about in a minute is how sustainable that particular product is, with 99% of the lead-acid battery being recyclable. So how does someone come along and choose a battery? What sort of reasons? It's generally down to total cost of ownership. So all those 4 battery chemistries that I talked about have huge benefits, and they also have, I wouldn't say downside, but there are issues with each one of them depending on the application. So I'm not going to read through all the things on the slide, but basically the application requirements are those in how much load, how much power is required, and also importantly, the shape of it, so the form, fit and function. That's really important. Where the battery is going to sit, either in a vehicle or in a home, in a factory, wherever they're going to be. That's really important because some of the batteries are lead acid batteries, for example. And again, whoever came up with the name lead acid probably wasn't a marketing person because it doesn't sound particularly appealing. But the acid in a lead acid battery generally is sulfuric acid. So, a dangerous chemical, dangerous acid. So, where the battery sits is, another reason why someone would pick a particular type of battery. There are choices of chemistry, types of electrolyte. There's surface area of the electrodes, and also safety and abuse. I mean, that's really important as well. How many of us charge and discharge our mobile phones, our laptops? We let them go to 80% and we recharge them, or do we go all the way down to 0% and then recharge them? What's the best for the battery? So again, they're all important parts, and also total cost of ownership. And probably cost, performance and safety have been really important, but then at the bottom there, recyclability, sustainability is becoming really, really important. So looking around the exhibition here, sustainability, decarbonisation, they're all really important areas. So I mentioned 12-volt batteries. The 12-volt batteries will support the 48-volt traction battery in an electric vehicle. The 12-volt is really important because it powers, apart from the wheels moving from apart from the wheels driving the car, the 12-volt system powers everything else. So in the old days, people of my age will remember 12-volt batteries that you topped up with distilled water. Now we've got more sealed batteries, and they don't just start the car and operate the lighting, but there's a lot of other things there. So consumers are looking for electric seats, big display panels within the car, lots and lots of electrification, so it powers all those loads, really important. When the car's parked, when the engine's turned off, there's still an awful lot of electrical work going on there. That's the 12-volt battery will support that, while the lithium battery is kind of resting. And most cars now have got connectivity across the into the cloud to have updates in software. All that's powered by this 12-volt battery that's sitting in there. The 12-volt battery becomes smaller potentially, but it's kind of called an auxiliary battery rather than the main battery in the car. That's the lithium product. I think the most important thing that I would say is the 12-volt system supports safety, and I think that's really, really important. It powers everything from the ABS system, the electronic driving capabilities, absolutely everything that's there. If the lithium battery fails, the 12-volt battery that is there to get us safely to the side of the road or work the brakes or do anything like that. So really, really important. So why not use a lithium battery in the 12-volt system? Well, perfectly possible. Absolutely, 100% possible. The advantage of lead-acid batteries are that they are particularly cost-effective. They're reliable. They've had, it says decades, but 150 years of experience of using these things, and they are sustainable. The lead, everything is recyclable within them. So it's possible that your Tesla could have a 12-volt lead-acid battery in it, and the lead in that could be 100 years old, could be more. It's a lovely closed recycling chain. Also, it's safe chemistry. There are horror stories talked about lithium batteries having electrical thermal runaway, overheating, catching fire. It's not as bad as I think people make out. We've all got mobile phones. They don't catch fire. I mean, every now and again there's an accident with that kind of thing. But if we're using reputable people, then it's always a good thing. So safety and reliability really important, and also the amount of data that's being produced by a car. That's also important, and that's the industrial side or the stationary side of lead-acid batteries that I'll touch on just a little later. So, quickly, lead-acid battery, what is it? There are basically three types of lead-acid battery. Flooded, which is, as it sounds, the acid is flooded within the battery. It moves freely. They don't charge as quickly. They discharge quicker. But they're very low cost. It's the lowest cost technology. There's the gel battery, which is the highest cost. So the electrolyte in a gel battery is in a gel. It's like phosphoric acid, but in a gel kind of format. Still maintenance free. Still really good in terms of charging time and discharge time, but they are expensive. And sitting in the middle there is the AGM battery, the absorbed glass matte battery, which is what I'm going to talk about now. It's maintenance free. They do charge quicker. They discharge slower. They cycle very well, and they're a reasonable cost. And the reason for all those properties really is the design of the AGM mat, so the non-woven component that's in there. So where does a non-woven fit? That's a simple schematic of a car battery. And there's an anode, a cathode, there's electrolyte and the separator. I'm pointing to the separator there. There's also a non-woven in pasting paper. Long story short, the lead plate is pasted with a mass that helps the electrical conduction, and the pasting paper helps hold that in place while the battery's being assembled. So again, lightweight non-woven, whereas the AGM separator is a little heavier. So, in an AGM battery, the non-woven is really important. It enables all those discharges and recharges, enables start-stop, but it doesn't do its job until it's actually in the battery. It needs to be designed to be able to be unwound in a manufacturing system. So like a lot of the products that we talk about in nonwovens, the job isn't done until it's in the product. And it needs to be able to withstand unwinding, so pressures. It needs to have some mechanical strength. It needs to be able to be cut easily. It needs to be able to be cut easily, but also be puncture resistant to stop any short circuits. So that's a balance. It goes into an enveloping. It goes into an enveloping stage in the battery design, and then stacked. It then needs to be able to be put under pressure and then release, and under pressure and release. So it needs to be elastic. So strong, elastic, easily cut, not penetrable. It's quite a design. Then it goes into the part where the plates are welded together. It's boxed again under pressure, so it needs to be able to pressure release. Acid fill is a really aggressive part where the battery's filled with acid. Needs to be able to withstand that. It needs to be able to stay intact while it's saturated with acid. And then the formation process produces a lot of heat. So again, the nonwoven needs to be resistant to heat. Markets. Some of the markets are obvious: cars, trucks, but also things like golf carts. So low-speed vehicles. They can be an existing market for batteries, which are really interesting. In the industrial side, so automotive is one simple sort of area to talk about. The industrial side, we've got stationary batteries and motive power batteries. So lift trucks, rail, all these guys have got forms of battery. In the rail and the aircraft industry, for example, sodium's a big component of the batteries. And then we've got reserve power, which are stationary batteries that are there for backup. I'll just move on to the next one. So mega trends, the reason for all this is decarbonisation, as we've talked about, but also not only decarbonisation, but the enhanced electrical load that produces in a vehicle. Lots of things have changed over the past few years in terms of the climate changes and the idea of getting to 2050 and having a climate neutral situation. In stationary batteries, again, there are more devices, there's more things need to be backed up. It's really important that hospitals, if there is a power shortage with a hospital, it's really important that there's a backup system there to kick in to keep things moving. Similarly with telecom systems, with the mobile phone that we all rely on, the towers are backed up by lead acid batteries. Finally, just some ideas for the future and some ideas that you may not think of. Just draw your attention to the more and more cars that are needed to charge as we move towards electric vehicles. Then that's going to be a huge pull on the grid. There are battery stations there, so kind of the battery station on the bottom in the middle, that is packed with lead acid batteries. They are there to provide immediate power when there's a dip in power, and a really important part of the infrastructure as we move forward is making sure that there's enough charge to charge the electric vehicles that we've got on the road. So I think I'm running out of time, so thanks for listening. And any questions, please give us a shout.
Thank you very much.
Thank you,
Ian, for your very informative presentation. Actually, we're doing quite well on schedule. If there's any burning question, there is time to raise a question. I know in this setting it's always difficult, but please don't hesitate later on to walk up to the speakers. But so then we proceed for now. But thanks very much for an informative presentation. And the energy transition is something, I find it intriguing, but it's also intriguingly complicated. What's good to know, nonwovens are here to stay. Also, no matter how we are going to power the world. and it gave a few very good insights. Next, because it seems as if we have decided to go to BEVs, battery electrical vehicles, but there is also the other technology, which is the fuel cell, and that will be the topic of our second presentation by Siddharth Shukla. He's a textile engineer. You know, textile, nonwoven, they're still pretty close. Based in New Delhi, India, and he is currently pursuing his PhD. It's nearly at an end at the IIT, Indian Institute of Technology in Delhi. This is also interesting. You're the recipient of the Outstanding Poster Presentation Award at the Nonwoven Innovation Academy, the NIA, the 2019 version in Denkendorf at the ITF, Germany. Recently, you received the Prime Minister's Fellowship for Doctoral Research in collaboration with Iloffic Industries Limited. And you have worked, your work basically is about the analysis of nonwoven structures via X-ray microcomputed tomography. And that's the topic also of today. But I've asked Siddharth to make it appealing for you, because if I say tomography, many of you think, oh gosh, but you bring it to life. Siddharth.
Thank you. Thank you. Hello, everyone. So Ian gave a very good presentation about how AGM separators are important, or how nonwovens are important for battery electric vehicles. So I'll be talking about fuel cells. So this is another aspect of basically mobility transition that we are seeing today here. So I'll begin with talking about mobility transition, how we are transitioning in terms of mobility. There are three pillars that I'll be discussing. Then moving on, I'll be talking about fuel cell electric vehicles, what they are, how they work, and then the fuel cell technology. So I'll breeze through all these things, and I'll end up on nonwovens in fuel cells. So fuel cell is something that is here to stay in the long run, because it is very close to internal combustion engine vehicles. And when the fuel cell is here to stay, so the nonwoven is also here to stay, because without nonwovens you cannot run a fuel cell, right? So about the fuel cells, I'll be discussing what type of fuel cell for nonwovens are used in fuel cells. I'll be discussing about their structure, how the wetting and compression properties help the performance of fuel cell, and what a microporous layer is and how it can be replaced by a nonwoven, right? I'll try to make it as generalized as possible, but so let's start with mobility transition. So mobility transition is nothing but the conversion of traffic and transport to sustainable and renewable energy resources. So there are three major pillars of mobility transition. I think we all know that. They are social, political, and technological. So I'll give a brief overview on social and political pillars, and then we'll discuss in detail the technological pillar that we are going to contribute in. So under the social transition, what we need is we need individuals that are opting for sustainable ways of mobility, right? So this is something that can be very visible throughout the Europe, right? We have seen people who are cycling their way to work, using public transport, and who are walking. So this is something that is the first step of social mobility transition, right? Now the next thing is that we need to transform the concept of streets. So as of now, the streets, they're considered to be a way to connect two possible places. But what we are seeing is majorly that streets are being converted into markets where people would like to walk. And numerous surveys have revealed that people want lesser and lesser cars on the street so they can walk and enjoy the view or the market and everything, right? So this is the second step of social transition. Now, the third step is actually very radical. That is to reduce the need to cover short distances in short time. Right? Because what do we need our cars for? To cover distances in a short time. We need to go to our work, we need to go and get some stuff, or we need to go for an emergency, right? And this is something that was never thought of before until COVID came into the picture. Because after COVID, people realized that, okay, work from home is possible. We can get our groceries while sitting at home. We don't need to go out for everything, right? So this is something that is, again, proven, and this is something that can be adopted in the long run. Now, moving on to political transition. So political transition is nothing but the formulation of policies that will promote the social transition that was shown in the previous slide, right? So a €9 ticket, this was very popular phenomena that happened in Germany. The entire public transport system was made accessible for €9 for a month. So this is a political reform that promoted social transition, right? So we need subsidized transport fares, we need better connectivity and percolation of various public transport systems. So this is something that is very evident in most of the major cities, but what we need is this percolation in places that are not very developed, right? Because if we take Europe for an example, Europe is a very developed area or continent, and we are talking about global transition, right? So globally, most of the countries are not yet at that level to have such a advanced public transport system. So that is what we need to come up with, right? Now, the next thing is that we need to somehow stop people who are still not listening. We need to somehow make them accountable that, okay, you are creating some pollution that needs to be stopped. So we all know what happens in London. If you go to the central part of London, you have to pay some extra taxes, right? So this is something that can be implemented in different cities where there is more crowd and more pollution is being generated due to vehicles. So this is a brief overview of political transition. Now moving on to technological transition, right? So what we are seeing is right now, or what we are contributing to as a Nonwovens community, we are contributing to the technological transition part, right? As Ian talked about batteries and battery separators, this is our contribution under the head of technological transition. So how the vehicles are transitioning from internal combustion engines to battery vehicles can be seen here. We started with hybrid electric vehicles, where the part of the power of the vehicle comes from a battery, and the major chunk came from the internal combustion engine still. Then we moved on to plug-in hybrid electric vehicles, where we had a battery that could be charged by plugging it in, right? So we had an engine, internal combustion engine, that partially powered the vehicle, and then we had a battery, auxiliary battery, that again shared some of the power. So these are partially electric vehicles, like some of the power from the combustion engine and some from the battery. Now coming on to fully electric vehicles, right? So you have heard about battery electric vehicles, BEVs. On the right hand side you can see. So battery electric vehicles, they have a very large battery pack that basically powers the entire powertrain front and back, and it needs to be recharged once the battery is discharged, right? I'd like to introduce you to fuel cell electric vehicles. Okay, so in the coming slides we'll be talking in detail about the fuel cell electric vehicles. Now moving on, this is a tentative comparison on fuel cells and battery electric vehicles. So the advantage of fuel cell electric vehicles is range and replenishment and weight. So range is basically how much a range can a vehicle cover on one charge or one refill. So you all know that with a battery, the range is limited. The range depends on the battery size, right? But with a fuel cell vehicle, since it is similar to a combustion engine vehicle, you just need to refill the fuel and the car goes along, right? Next is the replenishment. So even with the fast charge technology, we are working towards it getting faster and faster in our charging technologies, but still it cannot match what the petrol cars are offering, right? Because you go to a petrol pump, you get your tank filled instantly, and then you have the car running again. But that is not possible with battery electric vehicles, although it's possible with fuel cell electric vehicles, because it works very similarly. You just go to a pumping station, you pump in some hydrogen, and it gets running again, right? That's another advantage. Now the next advantage is the weight. So the bigger the battery you want, the more weight you have to carry it with yourself. And recently a very good colleague of me pointed out that even with everything else, with a fuel driven vehicle, as the fuel goes down, the weight comes down, right? But with battery, even if the battery is getting discharged, the weight is still the same. You have to carry that weight along, right? Now the next thing is fuel availability. So this is something where the fuel cell vehicles need to be worked upon, because we all know that hydrogen is something that is not very easily producible, or not a lot of people are producing green hydrogen. It is still gray. So on the other hand, electricity is coming from all of renewable resources. We can get it very easily. We can spread grids and make it more accessible. So this is something where a lot of work has to be put in, right? So moving on, next we have a detailed view of fuel cell electric vehicles. So what happens is there is a fuel cell stack that we can see. This fuel cell stack is connected with a fuel tank, which is basically hydrogen. It powers the fuel cell, and the fuel cell basically controls the drivetrain and everything. There's additionally an auxiliary battery, as Ian told that we need an auxiliary battery for emergency purposes. It is also to absorb or release some additional power that is required from the fuel cell, right? So this is a basic overview of what a fuel cell electric vehicle is. Now, moving on to the vehicles that are already in the market. So these are some of the commercially made vehicles that are right now running on the roads. Like you can see on the right hand side Hyundai Accent truck. So there are right now 41 Hyundai Accent trucks that are running in Switzerland itself. Right, so they are all working on fuel cell technologies, and all these vehicles are in commercial market. They are being produced for on mass scale. Okay, so obviously you can see that Toyota, Hyundai are the leaders in that. There are obviously a lot of companies that are working on fuel cell vehicles at a pilot stage. They are making some concept cars and everything. But in the market, you can right now, if you go out, you can purchase any of these. Right, we can on the bottom left hand side you can see fuel cell bus Toyota Sora, right? So this bus is very simple because it was inaugurated in the Beijing Olympics, and all the commute in the Beijing Olympic was done using the Toyota Sora fuel cell electric bus, right? Now these are some of the potential projects that are going on in terms of fuel cell. So on the right hand side you can see that there's a Alstom Corporation who is working on a fuel cell driven train. So they are trying to make the entire system based on a train system based on fuel cell. And on the right hand side you can see MF Hydra, which is a ship that is being planned to powered by hydrogen, right? So this is again a fuel. Both of them are potential fuel cell technologies that are being used. So this is again something where fuel cell has an advantage, because in large vehicles or large mobility systems, what you need is you need very high power that can only be achieved if it is a battery. It can only be achieved by a very large battery, which is again a very large weight, right? So fuel cell, what it offers lesser weight and quick refillability. Okay. Now, to deep dive a little bit more, let's look at the principle of fuel cell, how fuel cell works. So what happens is there are two set of reactions that are going on, one on the anode and one on the cathode. On the anode, what happens is hydrogen comes in as a fuel and it breaks down into H plus ions and electrons. While the H plus ions that you can see in green, they are passing through the proton exchange membrane. The electrons are passing from an outer circuit. So these electrons that pass from the outer circuit again go to the cathode and meet the hydrogen ion and the ambient air that's coming from the right hand side and form water as the only byproduct. So this is the complete reaction that uses hydrogen as a fuel and ambient air as a fuel from other side and produces water and heat as the result. Now, so far we have not talked about fuel cell nonwovens at all. We have only talked about fuel cells. Now if we dissect this fuel cell, if we look at each of the individual components, what we'll see is we'll see a bipolar plate followed by a gas diffusion layer, followed by a catalyst layer, followed by a proton exchange membrane, then again a catalyst layer, a microporous layer, and a gas diffusion layer, right? So what I'm going to focus on is the gas diffusion layer. So gas diffusion layer is basically right next to a bipolar plate where the hydrogen comes in and diffuses through the entire catalyst layer, right? So this gas diffusion layer is basically the nonwoven that we are going to talk about. Additionally, there are two more possibilities. Besides gas diffusion layer, we can apply nonwovens in microporous layer as well as the proton exchange membrane. So I'll be briefly talking about microporous layer here, but majorly about gas diffusion layers. Now, in the market right now, there are two types of gas diffusion layers that are available. One is carbon paper and one is carbon cloth, right? So the role of gas diffusion layer is to be porous, allow the diffusion of gases through the reaction chamber, conduct away the electrons that are being generated. Then obviously the water is forming that I've shown in the previous slide. So you have to remove that water. Otherwise, the entire reaction zone will be flooded. So once it's flooded, the entire performance of the fuel cell will go down, right? And again, the last thing is to provide a backing for the catalyst layer. So catalyst is basically a layer of platinum that breaks down hydrogen into individual ions, right? Now, in this presentation, we'll be mainly focusing on the paper and non-woven types GDLs. So there's carbon cloth, which is a woven cloth of carbon fiber that is used as a GDL. Then there's paper, there's recycled carbon fiber web, and then there is air-laid carbon non-woven, right? So if you look closely, the air-laid carbon non-woven and recycled carbon fiber web are typical non-woven geometry, right? Carbon paper is again paper geometry, but it is being quickly replaced by air-laid carbon non-wovens and recycled carbon fibers, okay? Now, what are the structural parameters that are important for a better performance of fuel cells? So the structural parameters go out to be the fiber volume fraction, orientation, port size distribution, tortuosity, and stereological parameters, right? So I'll be talking about further detail in about each of them, but let's have a look about how we can characterize our non-wovens to obtain all these properties and see if these properties are up to the mark or not. So there's a technique that we use personally. It is called the X-ray tomography. So X-ray tomography is a non-destructive technique that basically scans your non-woven, generates a 3D replica of the non-woven, and on that 3D replica, we can work to find out different properties such as pore size distribution, porosity. We can do flow simulations, and we can get the actual performance of the non-woven in terms of how is it going to impact the fuel cell. So this is a very good technique, and it has theoretically, it has a resolution of 10 nanometer per pixel. So 10 nanometer per pixel means you can scan a non-woven that has a fiber diameter of around 30 nanometers, right? But practically what I've observed is a 50 nanometer per pixel resolution. That means 150 nanometer of fiber diameter can be scanned with this technique, right? There are a certain commercial softwares that are available. We even have a stall of Geodict right over here on this floor who do this kind of work, do this kind of simulation. Now moving on, you can see the scans of different type of non-woven. So we have a non-woven that has a fiber diameter of 6 to 8 micron. We have a non-woven that has a fiber diameter of 1 to 1.5 micron, and a non-woven with a fiber diameter of 40 to 42 microns, right? So you can see all of these structures are very capably captured by this technique. Now, we have talked about the technique, we have talked about the structure. Now look at the individual properties of what we need for a very well-performing GDL, right? So we have the fiber volume fraction, which is nothing but the amount of fibers in a cube of non-woven, right? The percentage of volume occupied by the air in a non-woven, that's porosity, and if we subtract it by 100, we'll get the fiber volume fraction. We have the 3D orientation, which not many people talk about in terms of non-woven properties, because let's be honest, mostly what we talk about in terms of non-woven, we talk about the thickness, we talk about the GSM, we talk about the porosity. That's all we talk about mostly. But what we need to know is the 3D fiber orientation, because it is what actually governs the mechanical properties of non-woven. Next, we have the pore size distribution, obviously, which is very important, because a finer pore size distribution will allow more even diffusion of gases, whereas a coarser pore size distribution might not allow such diffusion, or might allow very quick diffusion, which is not required. Then we have the porosity, and we have two more properties, surface unit area and length per unit volume, right? So porosity is again something that is very important. Now this is something that is very unique to non-wovens. So non-wovens have a porosity of around, I'd say 90% or somewhere around that. In all the other structures that have a similar porosity of 90%, non-woven is the only structure that has a completely interconnected porosity. That is, all the pores are somehow connected to one another. Very few pores are left out, which is not the case in any other structure. Now, since all these pores are connected, if we want to go from one end of the non-woven, or if we want some of the gases to go from one end to the other end, what we need is the geometry of pore. If the pore has a very wavy path, it will allow more hindrance to the gas that is flowing through it. If it has a straight capillary, it will allow the gas to pass through easily. So this property is known as tortuosity, right? And not many people quantify the tortuosity of their structure, but this is something that needs to be looked upon. Then we have surface area per unit volume and length per unit volume of the fiber, which are again two properties that are very obvious because surface area per unit volume allows for more material to fiber contact, and the length again allows for a longer number of fibers to interact with it. So not to bore you much with this, I'll move on to two more properties that are called the 2D and 1D properties. So if we slice one of the layer of nonwoven, what we'll see is we'll see these kind of ellipses that are cut ends of the fiber, and if we draw some lines, we'll see how many points it's intersecting per unit length. So these are two properties that I feel that would be very new to most of you, because there is something that no one looks upon. But if we see fiber, if we see a 3D nonwoven as a stack of 2D slices, these are the two properties that need to be looked upon, because these properties will further allow you to assess the three-dimensional properties that I have shown you in the previous slides. So these are some mathematical equations that we have developed in our research group at IIT that basically correlate these two properties. Now, moving on, how these properties impact their performance of GDL in fuel cells, right? So GDLs, what they need is they need to remove the water that is generated at the cathode end of the fuel cell. For that, they need a very very complicated wettability behavior. What we need is we need a hydrophobic surface wettability, but we need a hydrophilic bulk wettability. That means if the water is on the top of the structure, the water should stay. But once it seeps into the structure, it should be immediately removed from the structure. So that's the kind of dual wettability that is required, and that is again only possible if we use a nonwoven structure. Now, these properties are basically governed by the structure of nonwoven, or the properties that I've shown you before. So that is the relevance of all those properties that what I have shown you before, right? So this wettability is basically controlled by the roughness of your nonwoven. So if we make a rougher and rougher nonwoven, on the right hand side, if you see, as we increase the roughness of the nonwoven, the contact angle is reducing, right? We are going from 128 degrees to 153 degrees. This is just done by changing the roughness of the structure, right? So to change the roughness, what we need to do is we need to play with the porosity and the fiber orientation that I have shown in the previous slide. So if we orient our nonwovens in a certain direction, that will certainly reduce the surface roughness of the nonwoven, because if we orient the fibers will come close and certainly reduce the surface roughness. And if we make more randomized structures, it will increase the roughness. And as we increase the roughness, what we see a rise in the hydrophobicity, right? So this is how the 3D properties that I've shown control the roughness and the wettability of the structure. Now moving on to the compression properties that I've shown before. So compression behavior of nonwoven GDL is another important aspect of the for the adequate performance of fuel cell, because what happens is that the GDL, when it is in a fuel cell, that is your nonwoven, when it is in a fuel cell, it is highly compressed. So upon that compression, what happens is that nonwoven tends to lose the compression resilience. So once it loses that resilience, what will happen is the contact between the conductive bipolar plate and the nonwoven will break. Once that contact breaks, the flow of current will also break. And the flow of current breaking means the performance of the entire fuel cell is going to deteriorate, right? So that's why we need nonwovens that are highly compression resilient, right? And that nonwovens can only be made if we use carbon fibers, high modulus carbon fibers, to make our nonwovens, right? Now, the structural deformation of GDLs is again controlled by obviously the structural properties. One thing that I'd like to point out here on the graph on the left hand side, there's a relationship between degree of anisotropy and porosity, right? So anisotropy is basically the property of any material that defines its directional invariability. So suppose we have a rectangular nonwoven and we select a point at the center of that nonwoven and we decide to go in any direction from that point. Whether the properties of that nonwoven going up and going down will be same or different, right? So if they are same, the more they are same, the more the structure is known to be isotropic, and the more they are different, the more the structure is known to be anisotropic. So as we compress a nonwoven, what we see is that the anisotropy of the structure is gradually increasing, which is again very uniquely only observed in nonwoven. No other material would change its anisotropy upon compression. And as I've told you, that when we compress the nonwoven, the fuel cell plates, they come closer, right? We need to have a compressed state of nonwoven, and if we compress the nonwoven, we'll get more and more anisotropic characteristics. The anisotropic characteristics govern how the hydrogen and water is going to be transported from the nonwoven, right? If we use anything else, suppose we are planning to use foams, we are planning to use sponges, or what I've shown, a woven GDL, all these structures will have the same level of anisotropy no matter how much you compress them. Nonwoven is the only structure that can actually change its anisotropy as they are compressed, because the fibers are aligned in a 3D fashion. Right. So the fibers are aligned in the 3D fashion. So once you start compressing the nonwoven, the fibers that are aligned in the 3-dimensional will start to come in plane. And as they are coming in plane, they are changing the anisotropy of the structure. So this is again uniquely only observed in nonwovens, and obviously it is very much needed for the fuel cell. So that is why we cannot ignore nonwovens if you want to make a functioning fuel cell, right? Again, on the right hand side, you see effective relative diffusivity that we see. So as we compress the nonwoven, obviously if we compress a nonwoven, the air will escape and the porosity is going to come down, right? This is a very general consensus that if we compress a nonwoven, the porosity is going to reduce. But once we reduce the porosity, what will happen is the pores are getting smaller as the fibers are getting closer. The interconnectivity of those pores is only allowed by nonwovens. So the gradual decrease in diffusivity that you see, this kind of decrease can only be observed in nonwovens, because if it is with any other material, the diffusivity will go much further below. Like if I'm talking about a compression of 40 to 45% in fuel cells. So once you compress a structure to half its width, the porosity is gone, the interconnectivity is gone. But in nonwovens, they retain their interconnectivity and they allow the diffusion of gases even at such higher compressions. So no other material except nonwoven is going to offer that, right? Now, this was all about GDL. Okay, so I think I have established my point pretty well that GDLs are nonwovens. If you don't use nonwovens, you can't make a good GDL or a gas diffusion layer. And if you can't make a good gas diffusion layer, you cannot make a good fuel cell. It's pretty established, right? Now what we need to look at is further where we can apply nonwovens, right? So GDL is something which is already being made by nonwoven, right? Which is nonwoven at its core. You cannot omit nonwoven with for GDLs, right? But with microporous layer. So right now what is happening is that our microporous layer is basically a deposit of carbon black particles. So what they do is they take a nonwoven and they deposit a layer of carbon black particles to create very small nano level pores, right? Which will allow a diffusion of hydrogen at a molecular level. But this is something, and obviously microporous layer, this slide basically depicts why a microporous layer is absolutely necessary. Because if you see in the diagram C, I would say, so this is a catalyst layer and GDL interface without a microporous layer. And if you see the diagram D, this is a catalyst and microporous layer interface. So here what you can see is that the water droplets in C are very big and water droplets in D are very small. So what happens is the droplets are small, they will not coalesce with each other and back diffuse into the reaction chamber and flood the entire reaction chamber. So that is why MPL is important. A microporous layer cannot be omitted in this case. Now what we can do is, right now you can see in diagram B, the microporous layer is basically very small particles, right? So what we can do is, instead of these very small particles, we can make electrospun structures or nanofibrous nonwoven structures, and we can carbonize them. Once we carbonize them, we get a nonwoven that is made of carbon fiber that is in nanoscale range. And now we have everything we need. We can just coat it over the initial GDL structure and we have a microporous layer that is again of nonwoven. So it is a hierarchical structure where we have coarser pores, coarser nonwoven covered by a finer nonwoven, right? Now, this is a comparison between the conventional microporous layer and the carbonized electrospin microporous layer. So what we get a very high porosity. We get a very high pore interconnectivity. Okay, so there's some issue here. Okay, so the second line is pore interconnectivity completely. We get a very high pore interconnectivity. Now the complexity of making a carbonized electrospin is very high. So this is something where the industry needs to come in and somehow make this process large scale. Otherwise, the covering of GDL with a particle bed is fairly easy. So this is where it's lacking, and I think it is something that can be worked upon. So with this, I'd like to summarize my presentation. So to summarize, I would say the fuel cells are very competitive options to advance the goal of electromobility and develop a hydrogen-based system. Nonwovens form an irreplaceable component of proton exchange membrane fuel cell due to their unique 3D architecture, obviously. Then what I showed is something called a recycled carbon fiber-based GDL, right? So what people are doing is they are getting recycled carbon fibers from different sources and they are needle punching it. So if it can be needle punch, it can also be air laid and wet laid, and a lot of techniques can be employed to make much thinner and thinner structures that can be again used as GDLs. Then we have nanoscale nonwoven structures that prove to be better alternative for MPLs in fuel cell. Consequently, nonwovens are essential for hydrogen power mobility system and in turn for mobility transition. So since we cannot omit nonwovens for fuel cell and we cannot omit fuel cells for hydrogen powered vehicles, we cannot omit nonwovens for mobility transition, right? I would like to acknowledge a few people here. I would like to acknowledge the industry that is sponsoring me and my PhD, that is Alofik Industries Limited. I would like to thank Mr. Kamlesh Kol, Sumit Sharma, and Danmin Singh, who have helped me a lot in making this presentation. And at the very end, I would like to give a huge thank you to Edana for allowing me to present my case here and prove to you all that nonwoven is something that is absolutely necessary for fuel cells. Right? Thank you.
Great. Thank you very much, Siddharth, for your wide presentation. Wide in the sense that starting from things that we recognize very well, boats, trains, cars that are actually driving in different countries already using this fuel cell technology, and then taking us along on the journey into what does it take. And we learned, I guess many of you learned, properties of nonwoven that go far beyond what we typically all know. Tensile strength, softness, because you introduced us into the world of the tomography, 3D modeling, compression strength, and the effects that it all has in the functioning of fuel cells. So thank you very much again. That brings us to the end of this seminar. We are well on schedule, so if anybody would like to ask any questions to our speakers, please feel free to do so. And I wish all of you a very nice day. Thank you very much. Ian?
Thank you.
Thanks a lot. Siddharth, great. Very nice.